In previous lectures, you saw that if we want to compute an numerical integration formula to compute the integrals, we have to solve a system of equations, and it was a very big problem for large numbers. But now we want to introduce a new technique to compute the numerical integration formula. So let me continue by numerical integration, and I want to use the Lagrange interpolating polynomial to compute a numerical integration formula. Before I start, please subscribe my channel and please try to watch online my videos. Okay, so let me start. We have some distinct points of an interval. So let x0, x1, 2, xn are n plus 1 distinct points in interval a and b. Okay, and Pn of x be a Lagrange interpolating polynomial, be a Lagrange interpolating polynomial. So, in fact, I can write f of x equal to sum I from 0 to n f I li of x plus, and I know the error term of the interpolating polynomial, that n plus 1th derivative of n at of f at eta x over n plus 1 factorial times pi I equal to 0 to n x minus xi, and also we know that li of x is the Lagrange polynomial, where li of x is the Lagrange polynomial. In fact, we talked about the Lagrange polynomial in the previous lectures. Now, let me rewrite this formula to this form. Now, let me tell something else. Now, take the integral from both sides, okay? Take integral from 1. Let me call it 1. What we get? The left hand side will be integral from a to b f of x d of x, and the right hand side, because the summation is finite, so we can move the integral inside the integral. So let me first write something like this: integral from a to b, I equal to 0 to n fi li of x, okay, d of x plus integral from a to b, here n plus 1th derivative n plus 1th derivative of eta x over n plus 1 factorial times I0 to n x minus x I d of x. Okay, so let me change the summation and integral place here, because the summation is in fact finite. So sum I from 0 to n, and I move out fi from integral, and I have just integral a to b li of x d of x plus, and also here 1 over n plus 1 factorial comes out of the integral, and just remains n plus 1th derivative of eta of x times pi from 0 to n x minus xi d of x. Okay, so this is the formula. Now, if I want to find a quadrature or a numerical integration formula for a to b, I just compute these integrals. Okay, and computing of these integrals are not very difficult. But before I start to compute some integration formula, let me write a definition for you. The degree of accuracy. Okay, so let me write the definition. In the above formula, let for I equal to 0, 1, 2, n, we define ai equal to integral from a to b li of x d of x. And also we define e of f be equal to 1 over n plus 1 factorial, okay, integral f n plus 1th derivative at ta x times pi I equal to 0 to n x minus xi d of x. So this integral from a to b f of x d of x can be written as I equal to 0 to n ai f I plus e of f, right? This is correct. Now, I can define the in fact the order of accuracy. Now we say a numerical integration formula has accuracy of order n if E1 equal to Ex equal to Ex to power of n equal to 0 and E at xn plus 1 not equal to 0. So it means that if you put instead of f here 1, this integral should be 0. Okay? if you put instead of fx again, this integral should be 0, and so on. So this is the meaning of the accuracy of a formula. Now, let me mention a theorem here. This theorem is very important when we want to compute, in fact, the error term. Okay? If pi I from 0 to n x minus xi in the interval a and b has a fixed sign, it means that the sign of this term, okay, does not change in the interval of the integration. It means that it can be positive or it can be negative. It's not possible in some parts of in fact, interval, the sign of this term is negative, or in the other part of the interval it is negative. Okay? Then there exists eta such that e of x equal to c n plus 1th derivative of f at eta over n plus 1 factorial. Okay? Where c is equal to integral from a to b pi a equal to 0 to n x minus xi d of x. This theorem is important, but we in fact we will not prove this theorem, and we just use this theorem to computing the error terms. Now, let me give you some special cases for computing the numerical integration. Okay, case 1. We want to compute the trapezoidal if I write correct. I don't know, it's not easy to write and pronounce. Okay. In fact, I want to compute a to b, f of x, d of x. Okay? Let n be equal to 1. So x0 should be a and x1 should be b, and also h is equal to b minus a. Okay? So integral from a to b f of x d of x should be equal to sum, or just because we have just two, we have integral from a to b, we put instead of f of x the Lagrange interpolating polynomial, and it will be x minus x1 over x0 minus x1 times f0 plus x minus x0 over x1 minus x0 times f1, okay, d of x, plus 1 over n plus 1 factorial. It means 1 over 2 factorial integral from a to b fn plus 1 f double prime at eta of x times x minus x0 times x minus x1. Right? Now let me do some do some computation for simplicity, and let me consider f0 come out, integral from a to b over x minus x1, it's x minus b over x0 minus x1 minus h. Okay, derivative differential of x plus f1 integral a to b x minus a over h, right, d of x plus half integral a to b f double prime eta of x x minus a times x minus b. Right? Now let me first compute this term. In this term, because x is belong to the interval of a and b, okay, let me write, since x belong to a and b, so x minus a times x minus b does not change. In fact, so let me write something here. The sign of x minus a times x minus b does not change in the interval a and b. So by this theorem, there is an eta in the interval such that there is eta such that here e of x is something like this. So such that 2 e of f be equal to integral a to b f double prime eta of x, in fact, times x minus a times x minus b d of x be equal to f double prime at eta integral as of from a to b x minus a times x minus b d of x. Right? We have exactly something like this. If you multiply these two parentheses and take integral, you will get f double prime eta times minus 1 over 3 x3 minus a plus b over 2x squared plus a b x from a to b, and if you used in fact the fundamental theorem of calculus for integration, you will get minus f double prime eta times b minus a cube over 6, and this one is in fact minus h cube over 6 f double prime at eta. Okay, so this is the error term, but now we need to compute these integrals. In fact, this integral, and also this integral. Let me do it. First, f0 integral from a to b x minus b over a minus b d of x. This is minus h. Okay, so f0 over h, I have a minus here, integral x minus b d of x from a to b. Okay, and this will be minus f0 over h times half x minus b from a to b. Right? Something like this. And this will be minus f0 over h times half times 0 minus a minus b squared. Okay? And this will be minus f0 over h times half times minus h squared, and if we cancel 2 by here, minus times minus is plus, so it will be 1/2 h f0. Okay, this is the first term. And also, if you compute the other term, in fact, a to b x minus a over b minus a d of x. Okay, so it will be f0 over h times a to b x minus a d of x, and this is half f0 over h x minus a squared from a to b, and this will be 1 over 2h f1. It should be f1, I guess. Yeah, should be f1. So we have computed everything that we need. Okay, so integral from a to b f of x d of x is 1/2 over h times f0 plus f1 minus h cubed over h here, h h cube. Yeah, it's correct, I guess. Look at here, I have some mistake here. So finally here, let me write something more. Finally, e of f should be, we divide both sides by 2, is minus h cubed over 12 times f double prime at eta. Right? So here it will be h cubed over 12 times f double prime at eta. That we are familiar exactly with this formula, and we saw this formula before. This is in fact the final form. Now let me try to compute the Simpson formula, the error term of Simpson formula, and also the Simpson formula by the Lagrange polynomial in the next lecture. Please subscribe my channel and follow my channel and try to watch online, and please wait for the next lecture. Thank you.